Today we're going to talk about the comparison of two means, which is nothing more than the examination of differences between two groups. It is more powerful than just looking at relationships, which is why you're probably going to really enjoy, as much as you can statistically, the t-test and the ANOVA and everything we do from here on out. The comparison of two means is really the very, very basic form of an experiment. You have an independent variable that has been manipulated in two ways, in only two ways, and you measure the outcome. So what happens is you have a control condition where you have this independent variable. Let's say we're talking about pavement, and we want a concrete pavement, and we want to look at the impact of different joint spacings. So everything else is same in that concrete pavement, and we're going with a typical joint spacing of 14 feet. We measure the stress and the strain in those pavements, and in the very next condition, we're going to change that joint spacing to maybe 20 feet, and we're going to measure the stress and the strain. So the only thing we've changed in that pavement is essentially the joint spacing. So that is our manipulation. And if that manipulation turns out to be effective, so the means are not the same, we will know that joint spacing does have an effect on stress and strain on pavement. And we can quantitatively say that without having to just put some wishy-washy terms around it like we had to with regression as well as correlation. So the t-test, essentially, we're taking that Pearson's correlation coefficient. We're going to be looking at using that for the effect size. We also used the t-test for the regression coefficients previously, but we're going to be looking at it a little bit differently here and a little bit stronger. But it's very similar to what we did for those regression coefficients. The question was, do they equal 0 or not? And if the t-test was significant, then they did not equal 0, which was good. So we could know that that predictor was important. We're going to do very similar things with regular old boring dependent and independent t-test. But I do want to talk about the difference between a dependent and an independent t-test. The dependent t-test, we're looking at related data. If you're doing human subjects data, you're going to be running those same subjects through multiple conditions. So that's the same sample measured at different times. Again, if you're looking at pavement, maybe you're looking at the effect of loads on pavement, so it's the exact same pavement slab, and you're just running different truckloads on that. That is a dependent t-test because the sample has not changed. The only thing that's changed is your manipulation. Sometimes we go ahead and we call this matched samples testing. Now, on the other hand, the independent t-test, sometimes you cannot have matched samples. So here we're looking at independent data. So let's say we were comparing, we'll go back to pavement. The pavement along US 33 as compared to the pavement along US 50. They are not the same sample. They are different locations, which means they're going to be independent data. So the big difference between the dependent and the independent is the sample is completely different. If your sample is exactly the same, you have to run the dependent t-test. The rationale for the t-test is essentially that we have to have samples that are from the same population. If we have samples from the same population, that means our means should be equal. And then our means can only differ because of chance. And so we're assuming that that chance occurs very infrequently, such as less than 5%, which is why we would choose a 95% confidence interval. So therefore, our null hypothesis will always say the manipulation has no effect on the outcome. That means the samples are from the same population. Now, normally we want our samples to be from the same population, but if we are trying to test that the manipulation is causing a change, for better or for worse, we do not want that null hypothesis to be accepted. So this is a case of generally most of the time we're trying to improve a facility, and we do want that null hypothesis to be actually rejected. Now, obviously, if you're trying to prove that something is equal, you want to accept the null hypothesis, but most of the time we're trying to find improvements that have otherwise not been found. The standard error is a really good way to be able to tell whether our data is variable or not and whether it's from different populations. If we have a standard error that's larger than expected, then we probably assume that we don't have any effect. The sample's really not typical of the population, and they're essentially from different populations. But the standard error it's much more difficult to understand, and as time goes on, as you start to understand what the standard error, a larger than expected is, you can get a little bit closer handle on the analysis, but for now you probably just can rely on the t-test portion. For the t-test, as the differences get larger, so we have mean differences, which SPSS is going to calculate for us. The larger those differences are, we can be very, very confident that the manipulation is what caused those differences. Now again, we want that chance variable to be very small, about 5% or less. So if we use our 95% level of confidence, we can probably say, well, at least 95% of the time we're very confident that that manipulation did cause the change, increase or decrease, in whatever outcome we were looking at. The test statistic is no different than what we've really been talking about before. The variance explained divided by the variance that's not explained. In other words, systematic divided by unsystematic variation, which is really nothing more than the effect divided by the error. Now, the error in the t-test is that estimate of the standard error of the difference. So hence, standard error, that's going to indicate it goes in the denominator. And the effect is going to be the observed difference is what we see minus the expected difference. But again, you don't have to memorize these equations. It's just kind of letting you know that statistics is very similar. Things don't change. A very basic form of the test statistic is not changing it at all whatsoever as we move through this semester. We do have some assumptions that need to be made. Obviously, normally distributed data. If we do not have normally distributed data, we're going to have to do something different. But for the dependent t-test, there is a slight difference. We do not need normal data. We need normal differences between pairs. So we can have two sets of data in the dependent t-test that the data is not normal, but the differences between those pairs are normal. And in that case, we can run the dependent t-test without loss of power. We also obviously have to have interval data. It cannot be nominal. For the independent t-test, we're going to have two other elements. We're going to have homogeneous variances, and we're going to have obviously independent data because that is the basis of the t-test, the independent t-test. All right, moving on to the dependent t-test, specifically, sometimes this is called the paired t-test, which kind of indicates that it's more of a matched set. We have the equation. So it's really just showing you that the difference in samples minus the difference between the population, and that population is mu sub d, and that's divided by the standard error of differences, which is you see on the bottom. The dependent t-test, we have that estimate of the population variance S sub d can be calculated as such, but again, you don't have to calculate this. SPSS will do this for you. All right, the dependent t-test, we have this average difference or the mean difference. That's going to tell us what experimental effect we have. It's going to tell us whether or not we have any systematic variation or unsystematic variation. We can go ahead and look at the standard deviation because that standard deviation tells us how good the fit of the mean is to our data. And the standard error, we talked about that generalizability before. That standard error is going to tell us how well is it a fit to the population. Now, when you divide by the standard error, you're going to standardize the difference, just like we did before. And when you standardize the difference, you don't really have to worry about what measurement scale we're looking at. So therefore, we can compare and contrast the difference between means that are observed and expected among multiple data sets. But the problem is if you're going to compare multiple data sets, you're going to lose a lot of power in your test, increase the type 2 error, which is not acceptable, and that's when we're going to get into the ANOVA. So if you have multiple data sets, we probably don't want to run a bunch of different t-tests, whether it's a dependent t-test or an independent t-test. If we have small standard errors, that's going to indicate that most of our pairs have pretty similar means, which means we can probably accept our null hypothesis. Large standard errors means the opposite, that things are different, and we're probably fairly confident that it may be by chance, but it's probably not. Alright, if the mean differences between the samples is really large and the standard error is really small, we are confident, absolutely confident, that the difference observed is not by chance and it must be due to the manipulation. So that's what we're really looking for, a small standard error that's small with a large mean difference. That large standard error gets a little bit confusing because it could indicate the same thing. That's why we kind of have to be a little bit careful when we have large standard errors. But again, that's a little bit more of an advanced technique. We're just going to rely upon SPSS to tell us a little bit more information that we need. All right, so how do you check normality for the dependent t-test? I said before we had to create a new variable, so it's the pairs of the difference between the two data sets. So we're going to find a new variable using that transform command, and then we can check the normality of that new variable. So we can have pairs that are non-normal, but that new variable, the difference of those pairs, be normal. So don't be too concerned if your regular data set is not normal. As long as you're doing a dependent t-test, you're fine.